I'd like to thank the organizers of this conference and of this workshop for putting together an excellent program, particularly during this challenging time. My name is Michael Posa. I'm an assistant professor at the University of Pennsylvania and a member of the GRASP lab. And within the GRASP lab, my lab is called the Dynamic Autonomy and Intelligent Robotics Lab. And I'll talk today about how we design simple models for legged locomotion that allow us to move beyond simple inverted pendulums. My lab at Penn focuses on enabling high-performance dynamic interaction between robots in the world. We're really focused on developing algorithms for that interaction, that contact, as robots are making and breaking contact with the world, whether that include impacts and friction for both locomotion and manipulation. We have work in a number of different areas, including some of these mentioned here in the slide. We've been working a lot on physics-based models. How do we understand and improve aspects of these models, as well as learning contact dynamics? How do we embed an understanding of discontinuity into a learning-based approach? We also have some very recent work on using tactile feedback to develop control policies that are provably stable for these hybrid settings. I mentioned here some of my older PhD work on optimal control and motion planning. It's an area we are still active in. But the topic for today is this one on the right side of the screen here, the simple model optimization. This is what we're going to focus on in today's talk. Okay. At the end of the day, the heart of most robotic walking, if I had to sum it up in a single sentence, was to say that most of real-time robotics, including walking, essentially is complexity management. We have some incredibly complicated mechanical system. In the case of our lab, we have a CASI bipedal robot, which has something like 24 degrees of freedom. The ambiguity comes in exactly how you handle the stiff springs and the closed kinematic chains within CASI. CASI has 10 actuators, 10 motors, has 4 springs. It has, in our model, at least 4 contact points, counting the heels and the toes on both feet. And it also has these 4 kinematic loops, which are closed linkages in the leg. Okay. And the basic problem for us as roboticists is how do we take a system of this complexity, the hybrid, high-dimensional dynamics that are inherent in it, and control those in real time. One very, very common approach, which I'm sure many people in the audience here are familiar with, is to use some low-dimensional embedding. For instance, we might use an inverted pendulum model, a linear inverted pendulum model, which takes this 24-degree freedom robot, compresses it down onto something like 2 degrees of freedom with 2 discrete actuators and a single contact point. Okay? And now that we're in this low-dimensional space, we can do all sorts of interesting control theoretic planning-based approaches. So just as one example, we might do something like reduced order trajectory optimization. So essentially real-time planning on the low-dimensional simple model. Very, very common with things like inverted pendulums. And then we take that low-dimensional plan and we lift it back up using a full order embedding back to the original high-dimensional robot. Right? And in that space, develop our controller for our torques U, our motor commands U, and then map that into the physical robot. The dynamics occur, and so on. And so this just gives one very, very common paradigm for how simple models ultimately get used to enable real-time control of our very complicated systems, right? And this is not really the focus of our talk, how you go about this process. It's something that many, many people do. Our question really is going to focus on the simple model itself. Okay. There's been a lot of really, really great success right in this realm. I'm just going to highlight one example here. This is a work done by IHMC, not my work, but a video that I really like. And this use of these simple models, things like inverted pendulums, has led to really a lot of success in the field. Right? A lot of these simple models have the flavor of imagine the robot as a point mass. Imagine the robot, all the complex dynamics of the robot can be compressed onto this very simple notion. And if you do so, what you get is some very simple and surprisingly robust algorithms, right? And these algorithms are at the heart of many of our walking control strategies. Okay? At the same time, if you imagine the robot's a point mass and perform your planning and control with this in mind, you're sort of limited to what a point mass can do, right? The use of these simple models ultimately does limit dynamic behavior, and aspects of the simple models ignore things like angular momentum or things like center of mass height, swing line dynamics, etc., ultimately aren't available as control mechanisms because they're not present in the simple model. Right? And so this is one reason, I would suggest, why we see such a huge gap between what humans are capable of. Here we see a video of some young men doing parkour, and our admittedly very, very impressive, but much less dynamic robotic performance. Okay? And so the question that we're trying to address in our research here is, how do we best, right? And the word best is very loaded, I know, but how do we best blend simplicity and performance, right? How do we operate on this Pareto curve between low dimensional simple models and high performance? And so to do this, we're going to try to answer two questions. Right? Question one is, can we quantify the performance or the capabilities / limitations of simple models? Right? Given a simple model, can I assess what its capabilities might be? How much is it going to restrict my dynamic performance? And then similarly, if we can do that, can we then discover new high-performance simple models, things that might be more useful for optimization or real-time control? Okay, so these are the two questions we're going to try to address. Okay, first, what do we mean by a simple model? Right? At a high level, we mean something that we can use for real-time planning, right? Typically much lower dimensional than the original physical system, and that we can then take a strategy developed on that simple model and apply it to the real robot. Okay? So that process looks something like this, right? Rather than plan with our full order dynamics, for instance, q double dot is some f of q dot u, and here I'll take q to be our configuration variables or joint positions, q dot the velocities, and u the torques. Our simple model might have some reduced order configuration and associated dynamics. So maybe our reduced order configuration is y. Our reduced order dynamics are something like y double dot, excuse the typo on the slide, is equal to g of y dot tau, where tau is now our reduced order input. Okay? Some other fictional input we've designed to apply to the reduced order system. Okay? And with this understanding of what a simple model is, we can define them via two things. We can define a simple model via the dynamics of that simple model, G, and some reduction, R, which maps from the full order state space, full order configuration, to the reduced order configuration. Okay? For example, we might think about a simple inverted pendulum model, right, where the inverted pendulum is representing the position of the center of mass. In this case, the mapping R maps from joint configuration to center of mass position. And then the reduced order dynamics G represent the dynamics of a simple inverted pendulum. Similarly, we might imagine a linear inverted pendulum with the same reduction, mapping from Q to center of mass, but then a different set of center of mass dynamics, in this case, those corresponding to the linear inverted pendulum. Okay. So for the rest of the talk, we're going to try to address those two questions from before. Right? And so the first question we're going to try to answer, and this is our preliminary work done a few years ago, was to ask this relatively simple seeming question, right? Which is to say, given that we know that simple models like the inverted pendulum limit dynamic performance, can we quantify what's lost? So for example, if we take some of the assumptions, for instance, angular momentum, right? And by reintroducing the effects of angular momentum to the simple model, can we significantly affect stability in this case, or performance? Okay? And so to answer this, we're gonna take a narrow slice of this question and say, instead focus on step recovery or push recovery and say, what set of states can be stabilized via bouncing and stepping? Right? If I have my simple model, I perturb the robot, and I use that simple model to try to recover, what recovery is possible and what is not possible? Okay? This goes back to this idea of reachability or viability. Right? We want to calculate the set of states that can be where balancing is possible, and then use that to compute the set of states where you can recover if you take a single step, if you take two steps, and so on. And of course, exact calculation of reachability or viability, long-studied problems in control theory, tend to be only tractable for very, very simple models. So linear models, very low dimensional models, etc. And once we start adding things like angular momentum, we're out of the realm of linearity. So in this work, what we used is convex optimization. In particular, we used something called sums of squares programming, which reduced it to semi-definite programming. Again, just a form of convex optimization. And we use this tool to compute inner and outer approximations of the viability kernel. Okay. So to find an inner approximation at a very high level, we essentially find a barrier function in control policy that proves positive invariance. You can think of this almost like a Lyapunov function, although a barrier function is slightly more permissive. Okay. This is actually a bilinear sums of squares problem because we have to solve for the control policy as well. Right? We're designing controllers using optimization and then proving something about those controllers. In this case, we're proving that a set of states, a set of disturbances can be stabilized. Right? This is a positive proof, right? Just like a Lyapunov function might give you a certificate of stability. Okay. For an outer approximation, we use a similar technique, in this case one based in occupation measures, which comes from measure theory, to prove that certain sets of states cannot possibly be stabilized. Right? This is a negative proof. That's the outer approximation. Okay? And this is a proof that exists for any control axiom. We're essentially proving that this disturbance is so big that no matter what you do, you can never possibly reach the upright balanced state. Okay? And this turns out to be a linear sums of squares problem. And the details of the optimization are in the reference papers, and they're not really critical for today, but I sort of want to give the high-level idea of why we have to compute both these inner and outer approximations. Okay? So we applied this to a few different models, right? We focused in this work on extensions of the linear inverted pendulum. We looked at things like varying center mass height, varying angular momentum, including impact models, right? And asked ourselves if the controller is allowed to leverage these effects, right? How does that affect our ability to stabilize from disturbances? We added these effects in alongside reasonable model limitations, things like acceleration limits and state bounds. Okay? And just as an example, if we allow both angular momentum and center mass height as additional degrees of freedom for our control policy, we can then compute these inner and outer approximations of the viability curve, of the set of states from which recovery is possible. So if we look just at balancing, which is to say the robot's not allowed to step, we get an inner approximation shown here in black and an outer approximation shown in blue. And this is to say, provably, using convex optimization, we have a control policy which stabilizes the set of disturbances in black. And provably, anything outside the blue cannot be stabilized. In between, there's a gap, certainly, that comes from the very nature of these approximations. But we have provable bounds on the capabilities of simple models. An approach that allows us to compare them explicitly. Okay? And we can do the same thing if we allow steps as well. So if we introduce the hybrid event, we can look at the one-step region, in this case an inner and outer approximation. Okay? What this does is it allows us, as I said, to provide an explicit comparison of these simple models. So on the left, we're looking at inner approximations compared, and on the right, outer approximations compared here via three different models: the linear inverted pendulum in blue, an extension which allows the center of mass to go up and down, and an extension which includes angular momentum as shown on the previous slide. And one thing we'll note here, say focusing on the right figure, is that allowing height as an extra degree of freedom has a very, very minimal effect, right? Provably, the red is the outer bound on what's possible with this model. And so if you're asking yourself whether you lost a lot by ignoring center of mass height as a degree of freedom in your model, the answer, frankly, is probably not. Right? Probably not. The benefits for reintroducing that at best are minimal. Okay? On the other hand, if you look at this reaction wheel style model that includes angular momentum, the effects are not huge, right? But they are noticeable, right? And it may be worth that extra degree of freedom, that extra complexity introduced by angular momentum, right? But what we've done in this work is really provide an explicit mechanism for computation of these bounds, and then therefore comparison, right, to better understand the limitations imposed by these types of models. Okay. Now, jumping ahead, to our work more recently here at Penn, I want to talk about how we actually go out finding these models, right? So it should be pretty clear for those who've worked in this space that these simple models, these inverted pendulums, capture some really fundamental aspects of Lakewood locomotion. Right? There's something that they fundamentally get, right, about this complex dynamical system. But at the end of the day, if you look at the literature, many researchers around the world have realized these models aren't quite capable enough. Okay? Some additional control authorities are needed, and this will therefore have to be added in via extensions of simple models. So this is where you get models with alphabet soup names like A-slip, T-slip, B-slip, 3OP, etc. All of these designed with very clear purposes, and many of them very successful in their own right. Okay? But the question we set out to answer was, well, given that there's this clear need from the community for extensions, right, can we design those extensions optimally? Right? Can we synthesize the best possible simple model? And to do that, we're going to look at our architecture as shown on the right here. Right? In an offline fashion, we're going to try to generate a new model. And we're trying to generate a model that's optimal, quote unquote best, and we'll define this carefully, across some particular distribution of tasks. So that might include variable speed, variable incline, variable turning rates, uneven terrain, etc. Okay. I'll note here, this is a pretty similar problem to model order reduction, right? But there's a key difference. And here is the fact that we don't really know a priori what regions of state space are relevant. Right? We need to design the simple model, right, which only has to be effective in some slice of state space across some slice of tasks. Right? The model has to be effective at doing things you want the robot to do, but without knowing exactly ahead of time what those motions look like. Right? So it's sort of like, to say it kind of loosely, it's like model order reduction, but we also have to choose what data to collect at the same time. Okay. So here we're going to walk through the overall process of model optimization and also include an example model, the linear inverted pendulum, on the right side of the screen. Okay. So as we mentioned before, simple models that we use are two functions. One is a configuration reduction. In this case, y, our simple model configuration, might be the center of mass position. We also have some reduced order input, which we'll call tau. In the case of the linear inverted pendulum with a foot, the tau might be the center of pressure's position on the foot. And then we have a set of reduced second order dynamics. In this case, those might be the center of mass dynamics of the inverted pendulum, where the center of pressure is controlled by tau. Okay? So how do we optimize over the space of models? Right? First, we're going to reiterate the fact that every model acts as a restriction or as a constraint. Right? Every simple model fundamentally limits the performance of the original high degree of freedom system. So we're going to try to find a model mu described by RNG, which is capable of the highest performance across the distribution of tasks. Which is to say, if I force my robot to act like the simple model, is it still capable of achieving a low cost or high performance over a wide range of walking speeds, ground inclines, and so on? So written as an optimization problem, it's an optimization over models, where the cost function here is the expectation over a distribution of tasks of the cost of solving a particular task when acting like the model mu. Okay. In this case, cost here, we compute via trajectory optimization, where we impose the model mu as a constraint. Okay. So cost, right, in this inner loop here, we solve literally via trajectory optimization, where we say along the trajectory, if you map from configuration to reduced order model, compute the reduced order model dynamics, those dynamics should be valid across the trajectory. Okay. And now we have a bi-level optimization problem. Right? We have an optimization over mu, and on the inner loop we have an optimization for each task, and we have this expectation. Because we have this task distribution, exactly computing that expectation is not tractable, but we solve this via stochastic gradient descent. So we sample some subset of tasks, we solve the associated trajectory optimization problems, we compute the gradient with respect to the model parameterization. In this case, we parameterize these models with a simple set of basis functions, and then take a gradient step and repeat. Here we're looking at a model of Cassie, a three-dimensional model of the robot, where we're optimizing a simple extension of a linear inverted pendulum. So we initialize our optimization procedure here with an inverted pendulum plus a controlled swing leg and ask it to optimize from there. This is over a four-dimensional task space covering a range of speeds, stride lengths, turning rates, and ground inclines, where we're using a pretty simple basis set, in this case quadratic trigonometric polynomials for both the model and its dynamics. Okay. Because we're still designing a low-dimensional simple model, this is something that we can then embed into a real-time planner, like, for instance, quadratic programming-based operational space control. The results are a little hard to visualize. What we're showing here is a slice of task space showing the performance improvement after model optimization, and we get a pretty solid improvement across the board, as well as actually a growth in the set of states for which we can, a set of tasks for which we can reliably plan motions. Okay, so ultimately, the dynamic range is increased as a part of this process sort of as a secondary effect. Okay, I'm really excited about this work. I think we're really kind of scratching the surface of this high level question of how do we decide what simple models we should be using? How do we remove the necessity for excessive amounts of human hand tuning and engineering into that process? I think we could apply this sort of technique not just to walking, but also to multi-contact manipulation and potentially other hybrid tasks. I think walking is a really great place to start, and we're still, continuing to push forward on this in terms of getting this onto the robot, in terms of really better smoothing out some kinks in the bi-level optimization process. But I think this really is something we're going to be working on for some time to come. Okay. All right. And with that, I'd like to thank all of the students who did this hard work, and particularly Yu-Ming Chen here in the middle has done a lot of the work that we've discussed here today. Jianshu Hu has been doing some additional work on the simple model side as well. I'd like to thank our sponsors, NSF and Google. The website's there if you'd like to check out more. And there's been a couple papers that are related to the work we've talked about today. So one published at RSS a few years ago, and more recently with Yu-Ming here, publication in ICRA just in 2020. Okay. At the end of the day, if I had to summarize our philosophy, I would say is that we want to enable high-performance dynamic robotics, and particularly focusing on that hard interaction between robot and the world. And I'll leave up some of these videos as I take any questions. Thank you very much for your time and attention. It's been a pleasure being here with you today.